Okay, this lesson is about L'Hopital's rule. This should really be called Johann Bernoulli's rule, but this is a nice little rule for calculating limits, right, if we run into some very difficult forms. And it's also a nice illustration of how important the derivative is in calculus. So I'm going to get right into the statement of L'Hopital's rule. This is kind of a strange looking rule at first. It should require some mathematical proof, but we will go through an example to illustrate why this statement is a pretty reasonable one. So first thing here is we have a couple of functions that are smooth. So these are differentiable functions. And what we're going to say is that we're trying to calculate some limit. So this looks back really at the old stuff that we talked about early on in calculus, right? Calculating the limit of the ratio of two functions as x is approaching a. So oftentimes when we try to find this limit, we get one of these forms in which we get very little information, right? So you let x go to a, and you might get 0 divided by 0, or some variation of large over large. So these forms are notorious when we calculate limits, and the problem with these is they give us no useful information. And oftentimes when you calculate a limit, this is what happens, but remember, this does not mean that the limit fails to exist. It just means we can't calculate it that way. So what L'Hopital's rule does is it gives us a very simple way of calculating the limit. So when we try to calculate the limit as x approaches a, what we can simply do, as long as the functions are differentiable, is to find the derivative of the top and the bottom, right? So we can see the difference here, f and g, and here we have f prime and g prime. And the key here is that the limits are exactly the same. So at first glance, this does look like a strange result. This latter limit, it's very, very important that this limit exists, or at least that if it's plus or minus infinity, something like that. But the important thing here is that we can differentiate the top and the bottom, and we expect to get the exact same result. So upon first glance, this doesn't appear to be one of those things that's necessarily true in mathematics. So our first example will illustrate this. But if you remember what the derivative represents, it does represent a rate of change or a rate of growth. So it's really telling you, if you look at the speed at which f and g grow, that it's reasonable that if you measure the ratio of those speeds, that is going to give you the same kind of information in the limiting sense as the ratio of the original functions. Okay? So just in words, all we have to do is to differentiate the top and the bottom separately. Right? The big warning here is this is not the quotient rule. So we're just finding f prime and g prime and then taking a look at that ratio. So let's begin with a nice example here. We'll go through the details here. And on this example, I'd like to talk about why it makes sense to talk about the derivatives, right? That ratio. So we'll spend a little bit of time to talk about the meaning behind this. So here's a good-looking problem here. So we're going to take the limit as x gets very, very big of this expression, x times e to the negative x. So if you just look at the expression itself, right, this thing right here, what we would first try is to let x get very, very big. And so we would really divide this into two separate pieces, right? We have two functions here. So as x gets very big, this x is going to explode, and this is exponential decay. So for x large, e to a large negative number, this is going to be very small. So the form that we get here is an interesting one. So we have infinity times 0. So we tend to think that anything times infinity, right, is going to be very, very big. So that would suggest this might be infinite. But on the flip side, we would tend to think anything times 0, right, is going to give us 0. And so that's why this is one of those indeterminate forms, but not represented on the L'Hopital's list. So what we're going to try to do here is to rewrite this in a form in which we can apply L'Hopital's rule. So we'll rewrite this here, right? Limit as x gets very, very large of x e to the negative x. And so what we can do is to rearrange this expression. So I'll take it up here. So the limit for x getting big, and we can write this as x over e to the x, right? Just expressing it with division instead of multiplication. So now if you try to check the form as x gets very big, this function explodes and the same thing happens there. So the form that we get here is an indeterminate form, right? Large divided by large. So this is one of the forms that is totally acceptable for L'Hopital's rule. So now to get into why L'Hopital's rule actually works, is if you look at this expression, you can think about the rate of change of the functions. So x is a fast-growing function, right? As x gets big, this is going to take off to infinity. But if you think about e to the x, this is illustrating exponential growth. So the bottom function here grows at a much faster rate, so it arrives at infinity, for lack of a better expression, earlier than the function x. So we would expect the infinity in some sense in the bottom here to be a much larger infinity. So what L'Hopital's rule tells us that we could do is we can measure the rate of each one of these and to see which one wins in some sense. So we're going to do that right here. Limit as x gets very big, and so we're going to take the derivative of the top and the bottom functions, and this is a very simple task, right? So x becomes 1, the bottom function becomes e to the x, and then if you let x travel to infinity, right, this is 1 over something very, very large, right? This limit here is going to be 0. So your limit in this problem is equal to 0, and that's really indicating that this bottom function grows at a much faster rate than this one here. So we can conclude that the original limit in the problem, right, this limit is going to equal 0. So let's swap problems here. We'll just do a couple more of these just to see how the rule looks on different problems. Okay, so here we go. This is an old type of problem you might recognize just by looking at it. If x approaches 3, right, the numerator here is going to give us a 0, and on the bottom we're going to get 9 minus 3 minus 6, so 6 minus 6. So this is good. So we get the an acceptable indeterminate form for L'Hopital's rule. And so you might remember with earlier techniques that you would try to factor the bottom and remove the x minus 3 factor, and then you get a revised problem in which you can insert x equals 3. And that's totally a good way to do that. But we're going to try L'Hopital's rule here, because the technique looks different. So we take this problem and we differentiate top and bottom. So the derivative here is 1 on the bottom, 2x minus 1. Right, so we get like an updated function. We're measuring the rate of the top and the bottom. And then notice here you can insert x equals 3. So the limit here will be 1 over 2 times 3 minus 1. So downstairs we have 6 minus 1. So this is really quick work, right? So you just end up with 1/5. So you should get the same answer here, right? If you try to factor the bottom and remove the x minus 3 factor. But that limit is quick work. Right, and it's mainly because L'Hopital's rule applies because you have one of the acceptable indeterminate forms. Alright, one more that we'll sail through, and that's it. Right? It's a pretty simple rule to use once you understand how it works. So this problem is off the beaten path. It's a little bit different, so we'll talk about why that is. So what we might want to do is just directly put in x equaling 0, right? X is approaching 0 from the right-hand side in this problem. So as x tends to 0, we get 1 divided by something really small, and that's going to cause this to be quite large. So the form that we're getting here, we have something large, and then we're subtracting. We'll check the other side. As x goes to 0, e to the 0 is 1. So again, we're getting something arbitrarily small here on the bottom. So we get this kind of nonsense. So we have to be careful with this because this is a large minus large form. This is not suggesting that this will equal 0, right? Because it really depends on the growth rate of these functions. Because this could calculate, in some sense, to almost any number in the world. So this, again, is not one of those forms that is on the list. So we're going to manipulate this expression to see if we can make it fit a 0 divided by 0 or large divided by large form. So let's do some manipulation. So I'm going to ignore the limit here and just look at the algebra. And then we'll go from there. So if you want to get a common denominator here, we're going to multiply these two, right, as our common denominator. That'd be the quickest route to take. So this first expression would be e to the x minus 1 over itself. So this would appear here. And then the second one you would multiply by x over x. So that would put an x right there. We have to watch the negative sign. So this is our updated expression, right? This is exactly the same as this, just getting common denominators. And now we do the same thing. We're just going to check the mathematical form. So we're going to let x go to 0. And so upstairs we're going to have 1 minus 1 minus 0. So we have a 0 here. And then x going to 0 here. Same thing is going to apply. So you can notice here the big difference, right? The way that the problem was originally written, large minus large form, and now if you just manipulate, we have an acceptable L'Hopital's form, right? 0 over 0, and that means you can just measure the rate of change of the top and the bottom, and then you can get to the bottom of this, right? You can calculate the limit. So let's do it. The rest of this problem we will dedicate to this expression right here. So this is the limit as x is approaching 0 from the right, and I'll repeat this. Okay, it looks like we have that. So we're all set, green light for L'Hopital's rule, and then we should find the limit. So we're going to find the derivative of the top and the bottom. So the limit as x approaches 0. Okay, the top will be pretty simple. E to the x, a 0, and then minus 1. So just like that. On the bottom you can do a variety of things. You can use x and e to the x minus 1 and use the product rule. So I'll just do that. So the first function and differentiate the second. And then we'll add the second, e to the x minus 1. And the derivative of x is 1, so we could just leave that just like that. Right, and then hopefully we can get an answer here. So when x is getting close to 0, this is going to be 1 minus 1, so 0 here. And then downstairs, e to the 0 is 1. So this is unfortunate, right? So we still have the same form, 0 divided by 0, but it is like this problem just resets itself, right? So we have an acceptable form, so we're going to use L'Hopital's rule one more time. So here we go. This limit here should be the same as if we calculate the rate of the top and the bottom. So upstairs the derivative is e to the x, and we just have to look at the bottom, use the product rule here again. So first and differentiate the second, and then we'll add e to the x, and then we'll get a 1. E to the x is never going to go away. That comes back. And then the 1 vanishes. So if you want to, you can simplify here, right? That's certainly fine, but I believe you can get the answer here just by letting x let x equal 0. So you're going to have a 1 here, right up here, and when x is 0, this term is going to vanish, right? That's going to be gone, and we're going to get 1 plus 1, so we get 2. So it appears our limit is equal to 1/2. So remember that this came from manipulating the original expression, one application of L'Hopital's rule, another application of L'Hopital's rule. And so we can come back to the original problem, right? And that was this one here. And we can conclude that as x approaches 0 from the right-hand side, this expression, even though it had the form large minus large, the limit is not equal to 0. It is, in fact, equal to 0.5.